Let's move on to multiple testing. So far I covered this and this. Now we're moving to multiple testing. So with multiple testing, let's say that we are running not one test, but m tests. So there's a there's some H01, some H02, all the way to H0M. So there are m hypothesis tests, and if we have a tolerance of type 1 error equal to alpha, so if we just reject each of them, if their p-values get smaller than than 5%, the thing is that the total type 1 error rate that we're going to have from this whole process is going to be much more than 5%. How much will it be? It's difficult to measure, but it's very easy to get some upper bound on the total type 1 error rate we're going to have. So let's define family-wise error rate as the probability of making at least one type 1 error when conducting m hypothesis tests. So this family-wise error rate, it's difficult to measure it, but if we assume the m tests to be independent, then family-wise error rate is going to be, it's equal to 1 minus the probability of so it is at least one type 1 error, so it's going to be 1 minus probability of no false rejections, or no type 1, making no type 1 error. So for each test, probability of making a type 1 error is alpha, probability of not making a type 1 error is 1 minus alpha. So if these are independent, probability of no type 1 error in m tests is going to be, so it's bounded by 1 minus alpha to the power of m, because for the first test we make no type 1 error with a probability of 1 minus alpha. For the second test, 1 minus alpha, and when we multiply these as independent, then the total that we get is 1 minus alpha to the power of m, and this thing grows exponentially with m. So if we plot it, if we plot 1 minus alpha to the power of m, well, if this error becomes larger than 5%, it's already a concern for us. But the thing is, not only it becomes 5%, it becomes much larger. So if we use alpha equal to 5%, and for the p-value that we get for this, we reject it when it's less than alpha. P-value that we get for this, we reject it when it's less than alpha, all the way to this. If for each of them we just compare to alpha, where m, number of tests, is 50, actually we're going to reach something almost equal to 1 with 50 tests, which means that the error rate is almost equal to 1. So we certainly make a false positive error. Is it clear? So this is where we use alpha equal to 5%. So you might be wondering, well, here are comparisons of the p-values from this test. We compare to 5%. So let's just compare to a smaller number. Let's compare to 1%. So if we compare to 1%, the same thing happens, it just happens later for more tests. So if we use alpha equal to 1%, we're going to have a plot like this. So actually it goes up much faster than this. Yeah, so let's say something like this. So even if we have a lower tolerance for type 1 error for each of these tests, same thing happens. It just happens for a larger number of tests. So changing this, like alpha, changing the value of alpha doesn't really help. So even if we go with 10 to the minus 3, we're going to have an error rate of 40% when conducting 500 tests. So this is when alpha is 10 to the minus 3. So regardless of how strict we are in terms of our tolerance for type 1 error, when we are conducting M tests, these errors, they compound, and our family-wise error rate, which is the probability of making at least one type 1 error, will be much, much larger than alpha. For example, instead of 5%, with just 50 tests, it becomes almost 1. Instead of 1%, with 500 tests, it becomes 1. Or instead of 10 to the minus 3, if we have 500 tests, it becomes 40%, 40% error. So pretty much anything above these lines are unacceptable. So for error, I think we have like a range like this that is acceptable for us. So pretty much all these data points that you see on this plot are telling us about something problematic. And what is problematic is that when we have multiple tests, type 1 error just compounds and becomes much, much larger than our tolerance. Any questions? I have the impression that you have a question. No? Is it clear? Which part is unclear? No? All right. So now for dealing with this family-wise error rate, we have two approaches. We want to control this family-wise error rate to the level of alpha, and one method is using Bonferroni correction, another method is using Holm correction. So let's start with Bonferroni. So with Bonferroni correction, the idea is very simple. The idea is that for the p-values that we get from those tests, we don't compare them to alpha, we compare them to alpha divided by m. That's it. So compare p-values to alpha divided by m. When we do this, this correction guarantees that family-wise error rate will be less than alpha. So there's another method, Holm's correction. It's a bit more complicated than this. I guess anything would be more complicated than this because this is very simple. When we have m tests, just don't compare to alpha. Compare to alpha over m, that's it. This one is a bit more complicated, but it actually guarantees the same thing. So also this one guarantees that family-wise error rate is bounded by alpha. So let me give you an example. So there's an example in your textbook about fund managers. So I think there's a table like this. So there are 5 fund managers. Each of them, manages a number of funds, a number of, let's say, collection of financial, securities and, financial assets. And for fund managers, it's important that they outperform the market. So in this data, there is some x. The variable of interest is excess return, which measures essentially how much the fund outperforms the market as a whole. So for each of these fund managers, we have some x bar, which is the average of the excess return of the funds that they manage. So the excess return for fund manager 1, so I want to just go with the numbers in your textbook, it's 3. For fund manager 2, this variable of interest, the average is minus 0.1, then we have 2.8, then we have 0.5 and 0.3. Then there's also some, standard deviation for the excess returns of the funds managed by each of these people. There's like some values. Then based on this X bar in the numerator and this S in the denominator, there's, some T statistic. Again, we don't need to worry about it. It's in the textbook. But the important part is that there's also a p-value, which pretty much summarizes the rest. So the p-value for the first fund manager is 0.006, then 0.918, then 0.012, 0.601, and 0.756. So here, for these fund managers, H0 is that this like excess return equals 0. So if a fund manager has a true excess return of 0 or expectation of excess return of 0, it means that they are not outperforming the market. They are equivalent to picking stocks randomly. So H0 is that, let's say mu equals 0. And so, I mean, if we do, if we do two-way statistical test, the alternative hypothesis looks like this, and I believe in your textbook it looks like this. But I think it also makes sense to have an alternative hypothesis that is one-sided, that says mu is larger than 0, because if they underperform the market, then that's really terrible, right? But let's say that we just want to see whether they have 0 excess return or non-zero excess return. So without any corrections, this is what happens. Without correcting for multiple testing error, essentially. So without any corrections, it's very easy. We just compare this to 5%, it's smaller. We compare this to 5%, it's larger. We compare this to 5%, it's smaller, larger, larger. So for these two, where p-value was less than 5%, so we reject H01 and H03. So for fund manager number 1 and for fund manager number 3, we reject the null hypothesis that says their excess return is 0. So we have statistically significant evidence that they are outperforming the market. So then from this test, maybe they get to keep their job or something like that, or I don't know, get a promotion. So this is, we have a binary decision about each of these fund managers. And only for fund manager number 1 and 3, we found statistically significant evidence to change our default belief that they are just picking stocks randomly. For the other ones, for fund manager 2, 4, and 5, we don't have statistically significant evidence that they are doing anything better than picking stocks randomly. But the thing is, in here, when we don't control for the family-wise error rate, we cannot guarantee that family-wise error rate is less than 5%. So let's say that in general in here, our tolerance for type 1 error is 5%. But the thing is here, the family-wise error rate, we cannot say that it's less than 5%. The family-wise error rate would be a bit higher. The limit that we can provide for it would be 1 minus 0.95 to the power of 2. So it would be, I guess, something around 90%. 1 minus this would be something around 10%. Sorry, it's to the power of 5, which is even worse. Can someone just calculate this number? 95 to the power of 5 gets much smaller, therefore our error gets much larger. Do you have it? 0.226. So error rate is 22%. This part becomes 78%, right? No, this part. This part is 20%, right? No. So the whole thing is 20%. All right. 22%. Yeah, which is kind of expected. It's something roughly like 5 times that 5%. So the error rate can be as high as 22%. How much is the error rate? No one knows. Because the true error rate, we can only measure it if we know the ground truth, which we don't know. Because this is about expectation of performance of these fund managers. So this is without correcting for multiple testing. Now, with Bonferroni correction, well, we just compare this not to 5%, but to 1%, because alpha divided by m is 1%. So reject, fail to reject, fail to reject, fail to reject, fail to reject. So we reject H01, and this method guarantees that now, with the process we followed for deciding on rejecting or not rejecting H0, now family-wise error rate is bounded by the tolerance we had, which was 5%. But there is one downside to this guarantee. The downside is that fund manager 3, we failed to reject the null hypothesis. So when we correct for multiple hypothesis testing, it's normal that we will have fewer discoveries. So whenever we reject the null hypothesis, quote unquote, we're making a discovery. Here, out of 5, we had 2 discoveries. Here, we only had 1 discovery. And that's actually the reason why we need Holm's correction. Because Holm's correction guarantees the same thing, guarantees family-wise error rate at 5%, but sometimes, and I mean usually, it allows us to have more discovery. Actually, it gives us at least as many discoveries as we would have under Bonferroni correction. So for this one, the process is a bit more complicated, but still, I think it's pretty intuitive. So first, we need to sort the p-values in increasing order. So we call them p1, p2, all the way to pm. So in our example, as it is in increasing order, this thing is p1, this thing is p2, right? Then this is p3, this is p4, and this is p5. We just sort these p-values in increasing order. Then we need to compare pj with alpha over m plus 1 minus j. Then when we reach, let's say, then when we reach some index, let's say index I, where we fail to reject, which means p-value I is larger than alpha m plus 1 minus I. When we reach a comparison that is failed to reject, then all remaining p-values or all remaining hypothesis tests are failed to reject. So as you can see, the process is a bit more complicated, but let's see what is the effect here. So this is P1. We need to compare it to alpha over m, because for P1, j equals 1, the denominator becomes m plus 1 minus 1. So actually with Holm, we start with something that is just like the baseline for Bonferroni. So we compare this to 1%. P-value P1 is smaller than 1%. So 0.006 is smaller than 1%. So we reject P1. We reject the hypothesis associated with P1, which means H01. Then the next number that we need to check is P2. So this is a sequential process. We need to go with this new order. We cannot decide about fund manager 2 now. We need to decide about fund manager 3. And that's the trick. So now we need to compare P2, which is 0.12. We need to compare it to 5% divided by 4. So actually the denominator, we just decrement the denominator in this process. So in this comparison, the p-value is smaller. Therefore, now we reject some null hypothesis which is based on P2. That null hypothesis is not H2, it's actually H3 because it is for fund manager 3. So it's H0 superscript 3. Then the next comparison is based on P3, which is 0.601. We need to compare it to 5% divided by 3. And actually in this comparison, the p-value is larger than the threshold. So we fail to reject. Based on P3, and P3 is associated to fund manager number 4, so we fail to reject H0 superscript 4. And then after this, everything else is also failed to reject. So without any comparison, then we can just say all remaining H0s are failed to reject. That's it. So now with this method, we get the same guarantee. The guarantee is the same, but we had 2 discoveries. One discovery here, one discovery here. So 2 fund managers get to keep their job or get promoted or something. So the result is different from Bonferroni correction. The guarantee is the same, the process is different, and in this example, the result was also different. Yeah?
Here it turned out that with Holm and without the correction, it's the same result.
Yeah.
So my question is, what's so bad about having a high family-wise error rate?
Well, this is some error rate.
Yeah.
So when we don't do this correction, in this example, the result doesn't change, but when you want to report this result, you cannot claim that you only had, your process had an error rate of 5%. In here, actually, your process could have had an error rate of up to 22%. We were just lucky that the result of this is equal to the result of this, and the difference is much more kind of clear when m is large. Here, m is just 5.
Why are we allowed to claim that? So how come we can just decide that version compared to alpha over m? There's some sort of...
But why we don't go with Bonferroni?
No, it's why are we allowed to? Why is Bonferroni allowed to basically?
Why is it valid?
Yeah.
That's actually a very good question. It's valid because of this. Why Bonferroni correction is valid? So family-wise error rate is probability of making at least one type 1 error. So it's equal to the union of these events making a type 1 error in test number J. So if you are concerned about probability of making at least one type 1 error when conducting M test, that's equal to the union of making a type 1 error in test number 1 or test number 2 all the way to test number M. So I have the union from J equal to 1 to M for making a type 1 error in any of these tests. So just the union of some probabilities is less than or equal to the sum of those probabilities. So let's say P making a type 1 error in test number 1 so all the way to error in test number M, right? So in general, probability of A union B is bounded by this. Because if there is an intersection, we need to subtract the intersection, right? So now if for each of these, if instead of alpha we have alpha over m, this thing will be equal to alpha over m, all the way to alpha over m, which is m times alpha over m, which is alpha. So family-wise error rate is guaranteed to be less than or equal to alpha. So this is just a very, I guess, simple way of controlling the family-wise error rates. But the thing is, this method, Bonferroni, is sometimes overly conservative. So the guarantee that it provides is based on some relatively loose bound. So it gives us this bound that family-wise error rate is less than 5% if we follow a process like this, which leads to only rejecting H01. But this bound is not a tight bound. It's a relatively loose bound. And because of that, here we are being overly conservative. That's why between these two methods, I think pretty much if we are concerned about how many discoveries we can have, we should use Holm's method. But Bonferroni method is the more popular method. I guess because it's just very simple. It just says when you're doing one test, it's alpha. When you're doing m test, divide the tolerance by m, right? So as this method is very simple, maybe 99% of time, people just correct the multiple testing error by just dividing the tolerance rate by m, which gives them this guarantee, which is sufficient, but it prevents them from making as many discoveries as possible while guaranteeing the same thing. But Holm's method, as you can see, we just need to go over a simple loop and compare these p-values, starting with the same threshold as in Bonferroni, but then decrement the denominator in each iteration of that loop. Other questions? So let me give you an example about using this actually in a data science context. So this example is quite a bit different from the topic that we were discussing. But the thing is, multiple testing is, sometimes just about good scientific conduct. Because when we are looking at this table, when we are looking at a table like this, it's very tempting to just say, all right, this one is significant. Let's report this in the paper, in the article, and forget about the rest. And if we are kind of, hiding some of the parts of our analysis, technically our family-wise error rate is this, but the readers of the article would not see the whole process and would assume that we only had one test and therefore our type 1 error is 5%. So this is actually something that many people get away with, because sometimes implicitly we're dealing with multiple tests, and then we report only some statistically significant result. Whenever we do that, we're pretty much being not fully honest. So this is somewhat about honesty. Also, when we have like some candidates for testing something, if we just go with some intuition and let's say, all right, let's just test one of them, even though that we have not explicitly tested the other ones, they were included in the process. And therefore, with good scientific conduct, we should test all the candidates and do the multiple testing correction. So pretty much, whenever you see some result of some hypothesis test, you can just, claim that they might have, had multiple testing error without noticing it. And most of the time, you are correct.
You clarify a little bit, like, how does that not just consider one case? When does the 5 case need to consider as a family-wise?
Yeah. So if you are in charge of making decisions or recommendations about 5 fund managers, then M for you is 5. You cannot just report this and say this one is significant, and not say anything about the rest. So the scope of the testing should be defined in advance and kind of registered and recorded.
But one of the first one was outperforming the market, right?
Yeah.
So we can say these two. Why would you compare it with another?
Well.
The other 4 are not affecting the result of the first one, right?
Well, they are somewhat affecting our scientific design. So let me give you an example. This is actually from a cartoon. So I will put a cartoon on Piazza, but there's it's a line drawing. It's a cartoon that that is about how jelly beans they cure some disease, right? So the cartoon is something like this. Someone says, we should test whether eating jelly beans cures this disease, and they do the test. And they found no statistical significance that jelly beans cure the disease, right? Which is kind of expected, and they had an alpha of 5%. But then, the first character comes back and says, no, apparently it's jelly beans of a certain color that cures that disease. So we should test this for all the colors of jelly beans. So they do 20 tests, one test for red jelly beans, and the test is, the result is fail to reject the null hypothesis. The null hypothesis is, of course, the default state of belief that jelly beans don't cure that disease. So this is fail to reject, then they test green, fail to reject, then they test blue jelly beans, fail to reject. But then when they continue this, right, at some point out of 20 colors, for one of them, they see statistically significant result, allowing them to reject the null hypothesis. And the thing is, then this one gets picked up by the media, some headline that jelly beans cures cancer, right? It goes to, so I'm trying to just redraw the cartoon, and that the newspaper says confidence of 95%, only 5% chance of coincidence, and this jelly beans cures cancer or something like that. So this is, of course, suffering from multiple hypothesis testing. So similarly, in the case of fund managers, when we have 5 of them, if we report result for one fund manager, we should also report for the other 4. And then it's clear that there were 5 tests conducted. Therefore, some multiple hypothesis correction is needed, either Bonferroni or Holm. Yeah, but it's very tempting, and I think it is actually a very common practice that people just try different ideas to see whether they give them, statistically significant result. If they get the result, they publish it or they report it. When they don't get the result, they just forget about it and not report it, not document it. This is an issue. This is an issue which kind of is also relevant to reproducibility in science, because many things, let's say, many failures to discover something is also relevant for good scientific conduct. So that's why we have pre-registration in psychology and I guess some other social sciences, because there was a reproducibility crisis in psychology. Just a few years ago, there was a famous, I guess a very controversial and influential paper that tried to replicate some results of some famous studies in psychology, and I guess maybe half of them did not reproduce, did not replicate. And one reason is because we just report the discoveries that we have based on statistically significant results, and not report failed projects or not report cases where we don't achieve statistical significance. So this is a very big concern in the scientific community. I think something that statisticians, they knew about it way ahead of these kind of popular discussions now between different fields. All right, so now I want to just give you an example about how I used multiple testing in a previous research project. So I was working with bill co-sponsorship data. So bill co-sponsorship data from the US Congress. So there's a piece of legislation, and there are names of some legislators as co-sponsors of the bill, which would be the people who have introduced the bill, right? And then the idea is that when we have all these bill co-sponsorship data, we should be able to get a network model of who is collaborating with whom. So, a model like this, where each node is a legislator, and each edge represents whether 2 legislators collaborate with each other more than what is expected by chance. So for each edge, we have one hypothesis test. So this is person A, some senator. This is person B, and then in a 2-year period of the Senate, they have co-sponsored, let's say, 200 bills, which means that there are 200 pieces of legislation that have names of person A and person B as the co-sponsors of the bill. So there are 200 signals of collaboration, but we cannot just use this raw number as the edge weight in here. For inferring a network model for this, we should do statistical inference. So that's why we compared this number to some null model, to some null distribution of what is the expected number of bill co-sponsorships between 2 legislators. So we just compared this 200 to that null distribution, and based on how extreme or how expected this value is, we decide that, all right, 200 is much more than what is expected by chance in a null model where legislators randomly pick which bills to co-sponsor. And then when we have statistically significant result, we're going to draw an edge between these 2 people. And that's how we get a network model. So then once I was talking to someone from statistics, I told about the model and everything, and she told me, well, how did you correct for multiple testing error? And at that time, I didn't even know what multiple testing is. Then I looked it up, then I realized, wow, for me, M was 20,000 because, well, I had I had Senate and House of Representatives. So for House of Representatives, there are 435 legislators. That's why we have 435 choose 2 pairs of legislators, and this number is huge. So I was conducting these many hypothesis tests and naively assuming that my alpha is 5% or 1% or something, so it's fine. All these edges that I have in my model are statistically significant. Because I was just comparing to that very naive and very wrong idea of just putting this 200 as the weight of this edge. So I was just thinking, all right, compared to that idea, I'm doing something, much more reasonable. But the thing is, of course, as m here was just a huge, I guess, maybe a 5-digit number, for me, family-wise error rate was very, very, very close to 1. So I was certainly making some type 1 errors, meaning that many of these edges that I had in my network were actually type 1 error, were a result of essentially observing some signal of collaboration between two people just by pure chance. Because I was just testing again and again, and this thing just compounded, so maybe a large proportion of the edges I had in my network model were just false positive. They were just edges between two people who actually don't have significant level of collaboration. Then, of course, I went back and I did the correction using Holm method. Any questions? Yeah? Yeah? So for rat blood pressure, it was just one test. We don't even need to do, we don't need to worry about family-wise error rate. So as long as it is one test, which is here, this is where we had one test, automatically family-wise error rate, automatically without any correction, would be equal to our tolerance, would be essentially bounded by our tolerance level, which is alpha. Two tests, you do either Bonferroni or Holm. Yeah? Yeah, that's just one test. Why would you do that 2 times? If you are doing, if you have one group, if you have like some baseline, let's say some baseline. So for me, the baseline was the null model. In the case of fund managers, the stock market is the baseline. If you have one baseline and then a number of groups of mice, then you're going to have one test here comparing group 1 to baseline. Group 2 to baseline, group 3 to baseline, group 4 to baseline. That's 4 comparisons. M is 4. Therefore, you need to do either Bonferroni correction or Holm correction. So in here where M is 1, you don't need to worry about anything. When we have multiple, M is larger than 1. And when M is larger than 1, then family-wise error rate without correction is, we don't have a guarantee that this is less than alpha. Questions? Yeah.
So I see this for family-wise error rate is about the whole process, is correct?
Yeah, exactly. So family-wise error rate is about the whole process, and that whole process is what we should normally register and not change. So if we run a study where we do these tests, and whenever they fail, whenever we fail to reject, we just forget about them, that's not good scientific conduct. We should do the pre-registration of these tests, and from the beginning, from the proposal, pre-register that these are the things, these are the kind of speculations that we have and we want to test them. And then M is fixed at that time, we do the test, and we also correct for multiple testing. Yeah. Other questions?
I have a question about the previous part.
Yeah.
You said that in real situation it's pretty rare when the two numbers are actually equal, right?
Oh yeah. So
how do we, if we want to, like, for example, the max, if a small amount of difference will be considered significant, like if we want to set some range equal to some range, how can we do this?
So the thing is, when you increase n, the power of your test increases, which is a topic beyond this course. But your test becomes more powerful of detecting even smaller amount of evidence. Yeah. It is as if you're talking about some more sensitive COVID test, which manages to detect even tiny amounts of viral load in our body, right? So with such a test, you're able to detect viral load more sensitively. And then, of course, if you take that to the extreme, any viral load will be a positive test, which is not good. You don't want that test. And with that test, of course, you can achieve a recall of 1 without doing anything biologically relevant. I can just run a COVID test here with a recall of 1. Do you know how I run it? Everyone that comes in, I say, you have COVID. Then I'm not going to miss any actually infected person, and my recall would be 1. Because out of relevant cases, which are infected individuals, I'm not going to miss any of them. But it is about a trade-off. Pretty much in all these fields, whether we are talking about medicine or data science or biology or binary classification or hypothesis testing, it's about having a trade-off between these errors, which is the same thing as having a trade-off between those desirable properties, trade-off between recall and precision and these sort of things.
So if we want to control the range with tolerance,
Yeah.
The only way is to adjust the number of samples. So if we want to give it a larger tolerance,
Yep.
the only thing we can do is to use less sample.
Yeah, so the power of test depends on a couple of things, but I guess the most important one is the size of the sample. So with hypothesis testing, the normal practice is that we have some tolerance for this and some minimum sort of expectation for the sample size. Like we say, any test with a sample size less than 50 or less than 30 is not valid. So we want to have some minimum n, and we want to have some maximum type 1 error rate, which is the tolerance for type 1 error rate, which is alpha. So these are two requirements for any statistical test. Yeah, and with these two requirements, we're trying to make sure that none of those extreme cases happens. Yeah, with this, we want some sufficient evidence, right? Not just any trace amount of viral load, right? And with this, we don't want too much false positive. We just have a low tolerance for false positive rates. Other questions? Yeah.
So that we can also adjust in the alpha, like the threshold to adjust the trade-off.
Which threshold?
For example, the COVID case.
Oh yeah. So yeah.
Instead of decreasing the number of samples.
Yes, exactly. So with a binary classifier, we have this threshold that we can move around, and of course we want to have it somewhere where the F1 score makes sense, or based on some criterion, depending on the context, right? But we can move that threshold because with those binary classifications, we get some p hat, and then it's a matter of what p hat do you consider evidence of positive case, right? In some other models, so in here we don't really have p hat, right? We have a test statistic, and as long as we're comparing that test statistic based on a theoretical distribution, it's just a matter of deciding alpha. And if it is some empirical, some sampling distribution, again, it's a matter of what point in this distribution do we call unexpected, or do we consider as unexpected? And this depends on the context. So this 5% is not really universal. Actually, in physics, people use much smaller p-values. I guess in the medical context, maybe 5% is somewhat expected. Yeah, but these numbers are really arbitrary, to be honest. So whenever you're going with 5%, you can also ask your question, should I go with 5% as the tolerance for type 1 error? Because in some situations, our tolerance could be lower, depending on how undesirable these two conditions are. So, right? In some situations, we care more about this. In some situations, we care more about this. So it's about finding that trade-off. Other questions? All right, let's take another quick break, and then we discuss false discovery rate.